Okay, here we go. Please go ahead and take out. So, welcome to class. We need our science notebooks, our Unit 12 packet, and your night and day chemical reaction worksheet from yesterday. You'll also want a calculator. Thank you for putting your phones on silent. Put them into your backpack. Take your headphones out. We have a full day today. A little bit of story time. We're going to do some demos.
What kind of story? We're going to watch Space Girl. Like, missing out on that. We're like 3 weeks behind on that.
No, we're not watching.
Turn my phone off.
We should. We should tomorrow.
Or like now.
We can catch up by
You gotta sit a whole day
Alright.
aside to catch up.
we almost do. How about I just make the link and you can catch up on your own?
No.
No?
I want to watch it.
It's not as fun.
Not as fun when it's not in class? Alright, fair enough. Here we go. Let's look at our agenda for the day. So, today is February, good lord. Today is May 9th. I'll be handing out your graded work on the counter. I need you guys to pause your conversations for me really quick. 3, 2. Was anyone gone yesterday that they did not receive the Unit 12 handout? 12. Alright, so our agenda is going to be working on, reminder, please make sure that you're working on those quick reviews. The quick reviews are also not all inclusive. They are a place to start. Please do not assume you can do only the quick reviews and you have officially prepared for the final. It's a place to do what?
Start.
Okay, take out your packets, look at your packets, go over the vocabulary, read the objectives. Can you state the collision model for theory, the collision model for chemical reactions and reaction rates, right? So that's why you kept them. So you can go back through them. Read through, add, polish, do that, Ben. That I can get you copies of them. And they would also have access online.
We have a quiz today.
We do not have a quiz today, that's from last week. Congratulations, no quiz. You guys need to update it. All right. What I need you to do now is take out your night and day lab packet. You guys did a fantastic job of using your time very wisely yesterday and pushing through to finish. I know that it was a push to the end, and I was really proud of how focused you were and got it all done, and also how well you picked up lab. So thank you. We were investigating rate and measuring rate as a measure of time, and looking at how changing concentration changed that. So what we're going to do is a little math magic where we just compare. We're going to do a ratio. So everyone has the time of the standard run. So Doug, what was the time of the standard run that you recorded? 57 seconds. And then from those 57 seconds, from that standard run, then we changed concentrations in different ways, measured what the reaction time was, and you recorded that. On A, B, C, and D below, your job is to do a comparison. So again, ratio. You'll calculate the comparison by doing the time of the standard divided by time of each trial. So the standard run was 57 seconds. Is that right? Okay, and what was the time for your first run?
25 seconds.
So seconds cancels out, and I'm going to get a relative number. So you just grab your calculator, do 57 divided by whatever yours is. You will record that under part A, so mixture 1 versus the standard. After you've done A, B, C, and D mathematically, I want you to write me a conclusion statement of how does concentration impact rate. When you're done with both of those, wait until both of you and your table partner are done. One person, whoever has the longer hair, is the one that's going to hand it into the top basket. All right, there you go. You are doing one number versus the other number, but this is what this says. All right. By doing the math in this, I'm trying to get my calculator to pop up. By doing the math in this way, my statement would say, this is trial run, was it run 1? Is that what we called them? All right. So trial number 1. this number is 2.28. If I wrote a sentence to make sense of this number, I would say trial 1 concentration was 2.28 times faster than the standard run. You with me? Okay.
Do you just want us to write that individually for each one, and that would be our statement, or do you want us to go to the bottom and write out our full statement?
I would like, you're welcome to make this statement for each of them. It really could be like a sentence, like trial 1 was blank, trial 2 was blank, trial 3, but then ultimately their conclusion paragraph should make sense of how is concentration and rate, how are they connected? And it should, so think of it as concentration increases, decreases, or does not change rate. With me? Okay.
How far, like, how many decimals do I still?
Let's do 3 significant figures. So I believe that would be 1 decimal point. All right, guys, in addition to concentration, no, that's not what I want. There we go. Go here. Old chemists never die, they just reach equilibrium. They're bad. I know.
Put that in your face.
Okay.
Turn and talk with your table partner. In addition to concentration, what other factors about reactions could we change that could change how quickly they proceed, their rate? So talk to your table partner, make a list. What else could we change?
Yeah, like how many more subjects we have compared to another.
Ooh. Is that like the ratios of like the two? Because you have more of one than the other. You're talking to your table partner on tap right now. Thank you.
Like, I could see where you're coming from. I don't know if they're the exact. Yep.
Describing reactions. Let's talk. And I want to hear from Tyler. Tyler, give me one variable or characteristic of an equation that I can change to change rate. What do you
This one's more of just a question first, and then I'll answer.
Okay.
Or like, because I remember learning about stuff in IPS with a catalyst work. Like, if you put in a catalyst.
Ooh, a catalyst. I don't know. So we're going to put that over here. Catalyst. And we're going to put like a little question mark because it's definitely something we've talked about before. It's not a new word, but it may be a word that not a lot of people yet know. Exactly. I could change the well, what about the chemicals could I change? I can't change the actual chemicals. What about the system could I change? Claire. All right, we can change their concentration. And from the night and day chemical kinetics lab, we made a statement about concentration. Cade, what did we say about concentration and rate? In what way? Increasing concentration does what to rate? Speeds it up. Increasing concentration, increase rate. All right, so make this list with me if you don't already have them on your paper. We'll write them down now. Let's hear from, here we go, this one. Claire, Zach, Yoakum. Zach, what do you think? What else could we change? About a reaction. I could add a catalyst to it. I could change the concentration of the reaction. What else could I do to make it go faster? Temperature. All right. We could.
My question. You didn't have to raise your hand, but thank you anyways.
All right, I've got it. Okay, we could temperature. So we could increase temp. And when we increase temperature, turn and talk to your table partner. What happens to the motion of the particles? What do they do? Trevor, what happens?
Start freaking out.
In what way?
They start going faster.
All right, they move faster. Okay. Increase in temperature. Allie, what happens to the motion of the particles? They move faster. All right, so increasing temperature increases motion of particles. Okay. What other factors? Doug, stopping here for a moment. Bailey.
Wait, did we ever get Doug?
Oh,
He's like never here.
Teacher moment.
I thought that was like.
Fair enough. All right. Bailey, what else can we change about the system?
Surface area.
Surface area. What surface area? Okay. How can I change surface area?
Spread out.
I can spread it out. I can crush it up. Good. So I can make the particles smaller, which increases their surface area. I can spread it out. That increases surface area. I can crush it, or spread it out. So scientific. All right, we can spread it out. Miss Hamilton, what can you add to our list? Stir it. You bet. We can stir it. And stirring it has a similar effect as increasing temperature did. It increases the motion of the particles, causing them to collide just a little bit more.
How are you when you rub stuff it gets hot?
That's yes and no. Yes and no. Oh, I totally will, I promise. All right. Let's see if Nathan can add anything else to our list.
I was just gonna say sir.
Okay.
We forgot about Doug.
Semi. Sorry, Doug. My bad.
Ben was the one who remembered.
I'm very grateful that you're in class, and I appreciate how you contribute to your team. So, Josh, anything else that you can add to the list?
Not really. Maybe like let it sit for a while. Is that one?
Well-
Slow it down. Freeze it.
If we want it, you're so right. So many times things just take time to react, right?
Yeah.
In our case, we're interested in not if the reaction will happen. We want to study how can we make it faster. Okay. All right. Anything else? Okay. So changing ratios, volumes, and amounts is absolutely something that we can do, and they all fall under the category of concentration. So let's keep this list here for a moment, and we are going to have a story time. We're going to head into the back. Now, here's the deal. If you're in one of the back two rows, I just want you to stay there, turn your desk around, stay in your seat, because You are as close as I want anyone to be. Fair enough? Otherwise, if you're in one of the first two rows, then we're just going to do little stadium seating. In other words, stand behind or have a seat or drag your chair, but no closer than where Kate is. Asians just hanging out in the back. All right. Lab. Test. I can get that to you. Very good. Felt better knowing some of the things. All right. What's that? We're heating it up. We're heating it up in preparation for a reaction. Okay, so we are going to look at some examples of the factors that we can change that could possibly speed up the rate of reactions. We're going to start first by investigating and not dropping. Reaction of ethanol with oxygen. Turn and tell your table partner what type of reaction is ethanol and oxygen. Ethanol and oxygen. Claire, ethanol and oxygen are what type of reaction? Single displacement, double displacement, oxidation, combustion, synthesis, decom. It's a combustion reaction. Well, and it's a little tricky if you didn't remember that ethanol is CHOH, like C2H5OH ethanol. Usually by lighters. Oh, thank you. I feel validated now. Thank you. All right. So in this wash evaporated dish, I have spilled ethanol. Okay. We turn the light off so that you can see this. So we observe that the ethanol is on fire, which we know is a combustion reaction. So ethanol in the presence of oxygen is combusting, releasing heat and what two compounds? Water and CO2. Carbon dioxide and water are our two products. If we wanted to increase the rate of the reaction, I can't add more. More just means it burns longer. If I wanted to burn faster, we need to do what? We could add something else, or we could I feel Zach cheering me on with the matches today, so I'm thinking we're gonna be okay. Right, Zach? Are you sending good vibes here to me? You're like, Fisher, it's just a match, you got this. Good Lord.
I guess I'm trying.
This is just a bad match. I appreciate your faith in me, Ryan. Clearly it must be the matches. Can't be Fisher today. Looks like she's done this before. There we go. Alright. If we want to increase the rate of the reaction, increasing surface area, right? So we saw the surface area in the evaporating dish, hot things look like cold things. Dutch, stop, example of spreading it out. So if we do this one more way, I have I like to take this moment to remind you, do not try this at home. I really mean that.
Ethanol, just like
All right. What type of compound is ethanol? It's an alcohol. What substance type is it? Polar covalence, which means that it has, in this case, non-polar bonds and polar bonds, and it will go from a liquid to what state of matter? Right. So we know this because every time I fill my gas, my kids are like, "I love the smell of gasoline." Yes. Who's ever said that before? Yeah, you guys have all said it. And if you can smell it, what state of matter is it? Yeah. All right. And then I tell them things like, "That's not funny. No, you don't like the smell of it, and that's your brain being starved of oxygen. So stop it." And I do all of the appropriate mom things at that moment in time. All right. So, all right, okay. So I'm dumping all of my excess alcohol out. Where is the alcohol still at? Where is it at?
in the sink. It's all lined in the bucket.
It's all lined on the inside of the bucket, and it's also in the form of a
Yeah.
gas inside of the bucket. So, I'm going to step this back onto my card. Can everybody see the bottle? Right? And we're looking for rate of reaction. And I'm channeling my inner match master. Alright. And we're going. Rate of reaction. Rate of reaction and note.
Oh,
Whoa, what is that?
water.
Water.
We just
It's
made water.
water. We just made water.
Does that taste good? Like actual water?
Well, it would, you can't taste water, technically. The water that we taste is the minerals inside of it, so it would be like little, gasoline flavored water. Alright. Okay, so would someone, oh so kindly, turn on the lights. Trevor, would you get the lights for me, please?
Yes.
Right
here?
Yes,
All three?
please. Okay. So we've observed. We've observed surface area, increasing surface area. So first we had only the surface area of the evap dish. We looked at rate. We looked at the surface of the counter. We looked at rate. I increased the surface on the inside, and we looked at rate. Increasing surface area just what to rate?
Speeds it up.
Speeds it up. Increases rate. So we are going to now look at a different reaction. This reaction is between hydrogen peroxide compound and a solution. Initial color. I mix them together. reaction or reaction. The gas is probably hydrogen gas. I'm gonna look at the reaction mechanism to answer that effect. Color. Now it's still there's some green in there too, but it's slowly turning back to this reddish pink. It looks pretty pink. It looked pretty pink before.
Wait, is that hot in there?
Yeah, I heated it up in order for the reaction to happen. What's happening to the green color? The green color. The green color is slowly fading. Would you agree? It's slowly fading? Yes? Alright. The reaction would have happened eventually. It was bubbling. Very slowly. I wanted it to go faster. And so I added a helper, a catalyst. Cobalt chloride. Catalyst can be inorganic, a salt. A catalyst can be organic. We call those enzymes. They're molecules inside the body that bring two macromolecules together to make a reaction happen. But what came back at the end of the reaction? The color, the catalyst. The color was the catalyst. The catalyst came back when the reaction was done. Catalysts only help reactions go faster. They are not consumed in reactions. They're not used up. They're not part of the reactants. They're not part of the products. They just make the mechanism, how it happens, go faster. So on our list, we had concentration. We investigated that yesterday. Temperature. We heat things up. They move faster. Surface area. We saw surface area. Stirring, we've done. Crushing, we've done. And catalyst is this last one. So let's head back to our desks. Take out our packet. Take out your packet for me, please.
All right. Here we go. Catalysts. In your packet, turn to the second page, please. We are on. Please pause your conversations. You are here with me. Today's date is 5/9. We are going to be on this page. Activation energy. All right. A graph is a model. Models communicate things that are happening that we can't see, that are too complicated to understand simply with words. So we graphically represent them to try and explain where we were and where we're going and how we got there. Okay? So this graph is a model that explains where we were, where we're going, and how we got there. It's based off of the collision theory of chemistry. The collision theory of chem, right here. The collision model of kinetics. So kinetics is a study of rate. It just explains how things happen. So here's a model that's trying to communicate that. We have nitrogen and ozone. And if nitrogen and ozone, or nitrogen monoxide and ozone, that are both in the atmosphere, and if they collide, but they collide in such a way that they do not react, they bounce off and maintain nitrogen monoxide and ozone. We would say this is an ineffective collision. It didn't result in a reaction because they were not the correct orientation. So in biology, we learn about enzymes. We talked about locks and keys, that they have to be in the right shape and they have to be in the right position in order for the reaction to occur. So if nitrogen monoxide and ozone collide in the correct formation, we get nitrogen dioxide and oxygen gas. Yes, Zach.
Ozone is O3.
Yes.
Can we breathe O3?
No, you shouldn't, because it creates this oxygen-free radical.
because it doesn't want to be O3, it wants to be O2, which means when it releases an oxygen-free radical, and that free radical causes damage. So ozone is considered an environmental pollutant in many cities. It's part of smog. You smell ozone when it rains. That fresh rain smell is ozone from the atmosphere. But no, we don't want to breathe it. It would be an environmental hazard. And when you breathe it in, those free radicals, those oxygen-free radicals, cause damage to cells.
So is that why it's called the ozone layer?
Yeah, the
Because
ozone
it's just
layer,
full ozone?
it has a higher concentration of ozone, and that ozone molecule absorbs light energy from the sun, creating oxygen and other byproducts, and it absorbs that ultraviolet radiation protecting us. If there's holes in the ozone layer, that radiation comes through, you have a higher chance of burning when you're outside from those ultraviolet rays. Yeah, so the ozone layer is extremely important in the functioning of our atmosphere, and adding ozone to the atmosphere in other molecules like CFCs, which were accelerants inside of hairspray cans, and also refrigerants in refrigerator units, all of those things disrupt this mechanism, and we can talk more about that in AP Chem, what's really happening. For us, what we want to understand is that there are ineffective collisions and effective collisions. Any mechanism that I do that increases the number of effective collisions makes the reaction happen faster. If I increase concentration, more of these guys means a higher probability of the correct collision. If I stir, that means that there are more reactions, meaning more opportunities for effective collisions. If I decrease the volume by increasing the pressure, I make more collisions, which will make more reactions. If I add a catalyst, I add a molecule in that will change the orientation or lower the activation energy, which means more reactions, more products. This theory, the collision model of kinetics, is how reactions happen. Thumbs up if you're with me so far. So this model is what we are showing in, nope, not that.
Whoa.
What? Do it again. In this graph. All right. So on your graph, I have my pen, I have a highlighter. Here we go. First off, on the y-axis is energy. Energy has the units of kilojoules, which are abbreviated kJ. Okay. The x-axis is time. And it's not literally like 1 second, 2 seconds, 3 seconds. It's more a here we began, here, and time proceeded. And we ended over here. So the amount of time is going to change. That is not clearly communicated with this model. It just says we started over here, and the reaction proceeds in this direction. Now, many reactions are reversible. So if I read left to right, I am reading in the forward direction. So this would be reading the reaction in the forward direction. If I read right to left, I am reading the reaction in the reverse direction. And both of these are valid. Okay. On my graph, reactants are listed on the left, products are listed on the right, and where this line is called the relative energy. And this line right here would be the relative energy of the products. And I could read it all the way over and see where it intersects this line, and it would have a number. So let's say, like, for example, this represented 10. And the reactants represented 100 kilojoules of energy, and this line up here was 400, right? Like there would be a scale on the left side that we could read. If I look at the reactants I have here, I have some carbon, hydrogen, bromine compound and hydroxide. And then what do we note about the compound at the top? Sierra, what do you note about the compound that's written up here? What have they done? Here I have some compound plus a hydroxide, and here what did they do? Sierra, do you see what they did here with this label? Like, what did they do to the hydroxide? They smashed it together, like combined it, right? Like the hydroxide's now in this compound. So this has a fancy name. This is the activated complex. The activated complex is a specific compound that exists for a very short period of time, and it's the intermediate or the in-between. When I went from reactants to products, this activated complex was that middle one. We saw the activated complex in the demo. Initially, the solutions were what color? They're clear. Then the catalyst was pink. I mixed them together and the whole solution turns green. The green thing, that green compound, was this. It was this activated complex. It had a whole different color. It has a whole different chemistry. Did it stick around until the end? No, it just disappeared, right? The activated complex has a short lifespan, and it is an intermediate step. Okay? It's an intermediate step. In our demo, this complex was green in color, and it showed up after they were mixed. It existed for a short period of time, and once the products were formed, the green color disappeared because the activated complex no longer exists. All right. Short lifespan, intermediate step. This would be the relative energy of my activated complex. So we have relative energy of the reactants, relative energy of my activated complex. Its position on the graph indicates its relative energy. And I have some relative energy of my products down here. We have this jump here, this huge jump in energy that's required to go from reactants to products. This jump in energy is called the activation energy. It is the energy needed for a reaction to occur. If this activation energy of 89.5 kilojoules is not met, no reaction happens. It doesn't matter if I have 89.0. If it's not 89.5 or greater, the reaction doesn't happen. Yes?
So if you wouldn't have heated it up, it wouldn't have gotten to the
Correct. Yep, exactly. The reaction would not have happened if I hadn't heated up the one solution. True. Which is fantastic, because if this fail-safe wasn't in place, every time you consumed food, your body was like, woohoo! We're going to do a decomposition reaction of those sugars, and everything would break apart. There would be no fail-safe keeping molecules and reactions from constantly happening. So this activation energy is like nature's stop sign saying, one, do we need you? Two, have you met all of the requirements necessary to actually occur? And it keeps systems in check. Okay, so that's your activation energy. All right, let's pause on that. And I need, what?
Wait, is that all you have written in the reverse direction?
Yes. Sorry, there we go. the reaction. I have test tube. And to my lab quest, I have a lab quest. Oh, let's do this. To the lab quest, I'm going to connect a temperature sensor. Maybe. I'm trying to connect. There we go. There's a temperature sensor in my lab quest. It's going to give me an initial reading. Yes, it could if I was measuring energy. It's not going to tell me energy. It's just going to tell me temperature of solution. All right. So we're going to collect some data.
What's the difference between measuring kilojoules and temperature, like water?
Temperature is a measurement of the motion of particles, and kilojoules is a measurement of total energy. And how are they different? And that is a fantastic question. And we study that in physics, and we study that in thermochemistry. And I'm going to have to let you be okay with not knowing the final answer yet. Okay.
I think I'm taking physics.
Are you?
Yeah.
Good. All right. To my hydrochloric acid, I'm going to add mossy zinc. So this is mossy zinc. It's a zinc solid, and on the surface it has this powdery coating on the surface of it. Thumbs up if you're with me. Right. We have a temperature. To my acid, I will add the mossy zinc. We observe formation of a gas. Agreed?
Oh, there it
You see it? Smoking, bubbling. And we watch the temperature of data collection. We're currently at 37.7 degrees Celsius, 37.8, 37.9. Feeling quite warm. All right. So when reactions happen, we can talk about their rate. We can also talk about how temperature is part of that component. So it is releasing heat to the system. It's getting hot. Energy is being released to the system. Where is energy going? In or out? Out, right? So we would say it's going into the system or coming out of the system, right? So it's coming out into the environment, leaving the reaction. And we see that it is now 39 degrees Celsius, and it's starting to plateau and level off, and our zinc is disintegrating. So now I have a solution of zinc chloride and hydrogen gas that left. Let's flip your paper to the next page. All right. In an exothermic reaction, exo means out, therm means heat. In a heat-leaving reaction, the energy of the reactants is higher than the energy of the products. This change in energy, this delta H, which is change in heat energy, will be negative. Why is it negative? Well, let's say that the energy here is 10 and the energy of the reactants was 50. When I do a change, I always do final minus initial. Final was 10 minus 50 gives me a value of negative 40. Heat is released, and that means delta H will be what sign? Negative. This is important to understand. Heat is a product. Heat energy is a product of this reaction. This was hydrochloric acid plus zinc chloride. Some energy was needed for the reaction to occur. We met that energy requirement. The final product was hydrogen gas and zinc chloride solution and heat. Okay. So endothermic reactions, heat energy comes out of the reaction. It will feel hot or cold? Hot. Feels hot. Exothermic reaction feels hot. This is not the first time we've talked about these. You should be like, this seems a little bit of a review right now. I've seen this before. We did this in reaction types in Unit 5. We introduced this in changes in matter in Unit 1. We did labs where we measured temperature and recorded them and said energy went in or energy went out. On the bottom of the page, we have a model for endothermic reactions. Endo means in, therm means heat. So endothermic means heat is going into the reaction. So here I have initial reactant energy, some activation energy, that's the difference between the initial energy in my activated complex up here, and my final product. Heat has been stored. Heat is absorbed. Where it went into the bonds, heat is stored in the bonds of the compound. This would be photosynthesis. I think that was a test question. Which of the following reactions would be an example of an endothermic reaction? It was like burning wood was one of the options. One of the questions, one of the choices was photosynthesis. Photosynthesis would be endothermic. This would be the formation of TNT, trinitrogen toluene. Any explosive, restoring more energy in than we had before. And it's explosive in removing it. It's the formation of ATP, okay, inside of your body. Storing ATP, restoring energy into the bond so that we can use it when we want it. So we have some initial enthalpy, initial energy, final energy, and this difference is the heat absorbed. And the difference will be a positive value. So if this is 50 and this is 10, 50 and 10, delta H equals final minus initial. Final is 50, initial is 10, and we get a positive 40. So the change in energy is positive, heat is absorbed. Okay. Activation energy is the energy needed for a reaction to occur. We've been reading all of these in the forward written direction. This would be the forward reaction, left to right. Our model is written in the forward direction, left to right. We read left to right in English language. This would be the forward direction. We can also talk about this reaction in the reverse direction. If I looked at this in the reverse direction, this reaction would be exothermic. The energy that I started with is greater than the energy that I ended with. And in the reverse direction, this would be an exothermic reaction. In the reverse direction, this would be an endothermic reaction.
So how would you reverse that?
Not all, but many reactions are reversible.
How could you reverse that? What you just did?
I cannot reverse this one, but we'll talk about that tomorrow. Like, how do we get things to reverse? Okay. Flip to the next page for me.
Hey, are you going to explain why stretch stuff gets hotter?
If you friction,
Yeah, but like,
why more? More than just friction is the answer? Forces, interactions between subatomic particles. Why you rub things and they get hotter? Yeah, the answer is friction. And what is friction? Friction is a force. And the amount of heat is based off of how sticky something is, or its coefficient of friction. All right.
why do balloons get static?
Electrical buildup. Yeah, from molecules bumping into them from the air.
But it's electricity.
It's electricity is just the movement of electrons. Anytime I can steal electrons from something and make them go somewhere else, I have moved electrons and I have created electrical flow, electricity. All right. In your graph, look at your graph for me really quick. You guys ready?
Yes.
I'll wait until you're ready. Ready? All right. In the graph, it's like a little hidden crossword puzzle. We see A, B, C, D, E, F, and G. Each of these letters indicates either a position on the graph or something that would exist at this location. So D, E, F, and G are changes. A, B, and C are locations. Something exists here versus the difference between these two places is. We have 7 statements on the left that match the 7 letters on our graph. Talk to your table partner and let's match them. And then we'll correct it as a group in a second.
What was your question?
Use your notes.
Sure, before we're gone. Yeah, I'll pull it up before we're gone. Once we're done, let's be correct. Once we correct, and I explain your homework. Are you done? No, you're not. What's your question, Ben? There's no T's.
What's under E?
Line.
When you look at it on the paper, it looks like it's
Fair enough. You mean F? You're here?
No, on the line of E, under right.
Go down. Oh, it's an arrow. Yeah, it's the
Oh.
bottom of an arrow. Yeah, fair enough. I'm with you now. Is that E would be the change in energy? Yes, ma'am. E is a change in energy. You're gonna say. Because usually I'm like. Alright, you guys ready to talk?
Yeah.
You've either looked at them, worked through a couple of them, maybe have a couple ideas. You might not be willing to commit to them because you might not know if they're right. Alright, let's look. Number 1. I need the activation energy of the forward catalyzed reaction. So keyword, catalyzed. A catalyst reduces activation energy. Activation energy is the difference between the energy of my reactants and the energy at the peak of the reaction. So I have 2 choices. It's either this jump here or it's this one here. Which one shows catalyzed? It's F, because a catalyst lowers the energy needed. Catalyst lowers activation energy. So it has to be this one, the lower activation energy. The relative energy of the reactants for the forward reaction. Okay, forward reaction means left to right. So here, is it A, B, or C? Which one are the reactants in the forward reaction? A.
Jaden. Pause. Do you have a question? Okay, then I need you to pause and correct yours and write down the correct answer. The relative energy of the products for the forward reaction. It's either B or C. Which one are the products? C. The change in energy for the reaction. That's going to be the difference between the energy of the reactants and the energy of the products. Which one shows the difference between these two positions? E does. The activation energy for the forward reaction. So again, forward means this way. Forward. So the activation energy of the forward reaction, it would be D. Right, the difference between here and here is D. The activation energy of the reverse reaction. So now I'm going this way. So it is G. This jump, I go back up. So G. And the relative energy of the activated complex, which letter indicates where the activated complex is found? Letter B, as in boy, activated complex is right here. All right, to the bottom. We have 4 graphs. Each graph, guys, turn around and pause. Each graph is labeled A, B, C, or D. You are going to use these as your answers for questions 8 through 17. So let's just look at them quick so that we're all on the same page on what they're saying. 2 of them are exothermic and 2 of them are endothermic. Talk to your table partner and identify which 2 reactions are exothermic and which 2 are endothermic. Exo equals out. Alright. 2 exo. 2 endo. Which ones are exothermic? B and D. Energy, energy, energy comes out. Energy, energy, energy out. Small. Alright. 2 are exo, 2 are endo. Let's hear from Ben. Which 2 are exothermic, Ben?
B and D.
B and D. Energy initial is just slightly over 300. Energy final is just slightly above 0. Energy initial is 100. Energy final is 50. Note the scale. Every box is worth how much?
50.
All right. Which means A and C are both what type of reaction? Endo. Endothermic. Endothermic. This would be very endothermic, and this would be slightly endothermic. The bigger the jump, the harder it is to reverse the reaction. The smaller the jump, the easier it will be to go back and forth both ways. So if you ask which reactions are reversible, it depends how big of a jump have we made. If it's a big jump, it's going to be very hard to go back up the hill. If it's small changes, it'll be easier. So the questions 8 through 17 ask about forward reactions. So that means left to right. Think of each of them as forward reactions. It will ask you things like which of these could be endothermic, which of them can be exothermic. So photosynthesis, we said photosynthesis was what type of reaction? Endothermic. A log burning would be exothermic, somewhat exothermic, or very exothermic. Very, it's on fire, not hot. It's on fire. Very exothermic. Okay? Slightly endothermic means might be a little cool. Very endothermic means lots of energy are going. Okay? The bigger the jump, the harder it is to reverse. Smaller the jump, the easier it is to go back up the hill. Go ahead and work on these now. 8 through 17. All you're putting on the list is A, B, C, D.
Could there be like multiple